Well, hello, Fruitport High School chemistry students. Welcome to today's lesson. So today's lesson is about the 5 different types of chemical reactions. As we end our course on our unit of chemical reactions, this is a lesson that you can watch, maybe take a little bit of notes and learn on your own. We will reinforce it with some demonstrations and lessons in class, but you should be watching this Monday or Tuesday at home. And get some paper out, write down a little bit about the 5 types of chemical reactions. They're really powerful for predicting what can happen if you're mix 2 things together. You can make a prediction accurately what's about to come, which is really powerful. You should also know that there's other ways to categorize chemical reactions. Some books will teach 3, some will teach 4, some will teach 5. I really like this 5 category way for beginners. I think it's the easiest to understand. All right, so let's start our notes today. So today's notes are on the 5 types of chemical reactions. And you're going to see today, oh, bless me. You should write down each title of the type. Maybe write down a little bit of information given about those and a couple examples. Okay, a couple examples. All right, so our first type of chemical reactions are what some books call synthesis reactions and some books call combination reactions. We use both because both are correct. I like the word synthesis because it sounds advanced, but combination is probably really appropriate. We're going to combine things. Synthesis and combination reactions are we build one large material, a product, from numerous small reactants. Okay, so here is a generic example of a synthesis or combination reaction where we have A and B turns into C. Now these are just generic examples. This is not carbon, boron, and an element with the symbol A. So let me give you some exact examples here. Okay, so one example is that if you took magnesium and you combined it with oxygen, you would make magnesium oxide. Okay, and so here are 2 small things making one big thing. And again, that doesn't have to be elements. We could have little compounds that come together. Okay, let me pull up some examples of that. So here's an example. What if we had I don't know, how about CaO? That's not an element, that's 2 elements together, and CO2. And so this is a small compound and another small compound that combines to make a bigger compound. This would also be a synthesis reaction. Now, we've recently talked about balancing chemical equations, and you might be a little bit uneasy that you see 2 oxygens here and 1 oxygen here, and that's okay. These are just skeleton or unbalanced equations sometimes. I don't want to put the big numbers in front, those coefficients, because that can kind of actually play with your mind a little bit, and you might see something that looks like a chemical reaction that's not a chemical reaction. Okay, so photosynthesis could be written down here. That would be a combination reaction too. And again, anytime you take something small, here's one that exists in nature, and you combine it with some oxygen and you make something bigger. All right, and this one here has 3 oxygens. Again, it's not balanced, but that's okay. All right, so these are examples of synthesis reactions. All right, that takes us to 20% of the way through today's lesson. Okay, the second kind of reactions that occur are decomposition reactions. And maybe you think of the word decomposing, right? And so sometimes we call them analysis, but I like decomposition. And these are the opposite of synthesis reactions. This is where instead of building something, we're breaking something apart, like decomposing, matter, a decomposing tree or something like that, right? And so if I took all these synthesis reactions and drew the arrow pointing the other way, took the reactants and the products and flipped them around, they would be decomposition. It's when one large reactant breaks down into smaller products. Here's a generic example. I got one thing, we call it W. I'm going to break it down into three things, some X, some Y, and some Z. So those are analysis reactions. Let me give you some authentic decomposition reactions that occur in nature, okay? If we took water, all right, and we could break it down into pure hydrogen, remember hydrogen's diatomic, and pure oxygen, remember oxygen's diatomic, this would be a decomposition. One bigger thing broke down into two smaller things. But it doesn't always have to be elements. I could make something like this, NaHCO3, that's just one big complicated compound, actually can break down into this compound, which is smaller, and carbon dioxide, which is a smaller compound, and water, which is a smaller compound. So you don't have to break down into elements. It's common. You could take, iron sulfide and break it down into pure iron and pure sulfur. And that would count as a decomposition, but it doesn't have to be elements. Okay. All right, 40% done with today's notes. All right. The next one we have is quite different. We call this one single replacement reactions. And let me start off with an example. Here is A, an element all by itself, and B and C are linked together, chemically bonded together, and there's a change. Now, A is connected to C, bonded together, and B is left all by itself. All right? And so this is where single replacement reactions are when one element changes what it's bonded to. All right. Here's a silly example using real people. All right. Here's Jen and Brad. They're a couple. That would be like the BC, a couple together. And Angelina is all by itself. That would represent A. And then there's a switch. Brad switches partners. Now Jen is stuck by herself, and Angelina is with Brad. Okay. And so single replacement reactions are really, really common in the chemistry world where one element changes places. So let me give you a couple examples of that. You could have something like iron that's all by itself and silver attached to chloride, and it switches so silver is all by itself and the iron is attached to the chloride. Now again, don't get distracted by the number 3. This 3 is because of all the crisscrossing of charges. You should focus on what elements are where, what elements are partnered. Do you see a single person and a couple? And now we have a new couple and a new single person. This is kind of what's going on here. Okay. You could also have this with, I could have Na plus KBr, and it changes to be NaBr and K. Now this is very similar to the one above. The bromine is switching partners. It doesn't matter if I put the K first and then the NaBr. Like these two products could be switched around. Just like 2 plus 3 is the same as 3 plus 2. You can switch that order around. Sometimes people get uncomfortable when polyatomic ions get involved. So what if I gave you lithium and I gave you gold nitrate? And so here's lithium and here is gold. And remember, this NO3 should be thought of as one thing we call nitrate. And it turns into lithium nitrate and gold. You can see the nitrate switch from gold to lithium. It's got a new partner. This is called single replacement reactions. All right, that's 3 of the 5 done. We'll just keep charging along here. Our next one is double replacement reactions. And double replacement reactions are where 2 elements change place. So you see we have like a little partnership, like a little couple, a little bond, J with K. And we have another one, L with M. And then the K and the M both switch partners. And so the J and M come together like this. And the L and the K come together like this. So it's a lot like single replacement, but we have two elements changing what it's bonded to, where it's located in the reaction. So if I wanted to give you some double replacement reactions, these are pretty common in the lab too, right? I could do this. Let me give you one where there's no polyatomic ions first. What if I gave you NaCl and I gave you LiBr? And what would happen is the Cl and the Br change spots, and the Na is with the Br, and the Li is with the Cl. Hopefully you can see it. Looks like a little couple and another couple, and they form some new couples over here. Now, sometimes some numbers can get involved, and that throws students off. Don't let that throw you off too much, okay? Because the numbers are there for crisscrossing purposes, not for double replacement purposes. So what if I gave you AlF3 with CaO? Well, now the Al is going to be with the O, but if I do the crisscross, it would look like this, because aluminum's positive 3, oxygen's negative 2, and calcium would be with fluoride. There we would need 2 fluorides, negative 1, to balance out the 1 positive 2 calcium. So you'll see the numbers don't match up. It's not a balanced equation. Ignore the numbers to see the double replacement. Just see how the F and the O switched which partners they bond with. Okay, and it can happen with polyatomic ions. So if you had, I don't know, strontium sulfate, and it was combining with potassium nitrite, you might get strontium nitrite. I know I got some little parentheses because of crisscrossing going on, and potassium sulfate. All right, and again, there's some numbers. So two things can switch places. All right, and our last kind of reaction is a combustion reaction. Combustion reactions, and when you take something organic, that means, oh, I said organ instead of organic. Let me rewrite that. Organic, which has carbon, and you burn it with the oxygen in the air, and it always makes these two things. Sometimes it can make a third thing, but this is combustion reactions. If you have propane at your house for a barbecue or something like that, this is the equation. Propane plus oxygen makes carbon dioxide and water. Okay. Again, what if I gave you something that was C2H7N? What if I threw an N in there and I still burn it with oxygen, and I'm still going to make carbon dioxide, and I'm going to still make water, but I'm going to have to make something with nitrogen, and I think it makes nitrogen dioxide, okay? And so you might see that it's a little bit different, but it's got these 3 components: oxygen, carbon dioxide, and water, even if there's some other things that get thrown in advanced ones. All right, well, that is our lesson for today on the 5 types of chemical reactions. Study those, look for the key patterns, and in your homework today, all you have to do is go to Google Forms, look at some fact, or look at a sample and decide if that goes with synthesis, decomposition, single replacement, double replacement, or combustion reactions. All right, we'll see you in next class. Email me if you got any problems.